Hello, my name is Dr. Kevin McGarrigle. I am the coordinator and principal instructor for the National Advanced Silvicultural Program, or NASP, Module 3 on landscape ecology. Specifically, this course is focused on applying the principles and tools of landscape ecology to ecological forest management, and even more specifically on understanding and managing how vegetation patterns, both in terms of composition and structure, affect various ecological processes and desired outcomes. Those processes can be almost anything. They could be referring to the spread of a disturbance agent, such as a fire or an insect or disease pathogen. They could refer to the movement and habitat suitability of a focal organism, perhaps a TNN species or a management indicator species or a game species or other species. It could refer to something more general, such as maintaining the resiliency of the forest to natural and foreseeable altered disturbance processes. It could be something very general, such as sustaining the native biodiversity. So when I refer to vegetation patterns and how they affect process, we're actually referring to a wide variety of things, ranging from very focused processes to very broadly defined quote processes. And we'll, of course, talk a great deal about the details of what is encompassed by the idea of pattern and process when we meet in person in the course. But the focus of this short video today is to help you or to help clarify the expectations for your data prep on your home unit. You will have all received the pre-work document that describes in detail what you need to do in advance of the course to adequately prepare for the course. And one of the major components of that pre-work is for you to develop a data set for your home unit, and specifically a data set representing a project that you have been involved with ideally, perhaps one that you're currently working on or perhaps recently have finished, or in the special cases where you haven't yet been involved in a project, using somebody else's project on your home unit, whether that be the forest you're on or another forest within the same region. It doesn't really matter for the purposes of this course. What's important is that you come prepared with a data set that you can personally relate to on the ground. The project data set should or could either represent a project that is in the planning stages, where you are designing and planning the layout of the project and writing prescriptions for how to implement the project and so on. Or it could be a project that's already been implemented. So you have essentially designed the project, it's been implemented, and now you're in a position where you can evaluate the pre and the post treatment effects. What's really important for this home unit project is that the data set represents vegetation patterns that have enough complexity so as to meaningfully address how those patterns may affect one or more of the focal ecological processes. And what you're seeing on the screen here is an example of a data set. It comes from the Coconino National Forest in northern Arizona, just outside Flagstaff. It's a focal landscape that we will be visiting in the field during the course, and I'll be using at times to describe some of the concepts and some of the tools that we'll focus on in the course. But what you see here is a project area outlined by the solid boundary here that's several thousand acres in size. And the size of the project area really isn't that critical, but typically it's going to be in the several thousand acres to potentially many tens of thousands of acres. That really depends upon you and your home unit and the project you might be involved in. What's most important is that your project area include enough complexity in vegetation patterns to basically be able to see and discuss and evaluate how those patterns may be affecting the ecological processes or desired outcomes. So that's really the most important thing for you to consider is try to make sure you have a landscape and one or more vegetation attributes that shows some ecologically meaningful pattern. Otherwise, it's sort of a mood exercise. If this landscape had, let's say, 2 or 3 or 4 patches of vegetation, there's just not a whole lot we can do at that scale and with that low level of complexity. So that's the most important thing. In the pre-work document, I said really you should be looking at a minimum of, let's say, 25 vegetation stands, but ideally more is better. And what you're seeing here within this project boundary, outlined by these dark lined polygons, are the stands that are part of the district and the forest stands layer. And most of you will have a stands layer such as this. It may not be called that. And if you're not in the Forest Service, you may have a vegetation layer that's it's defined and described differently. But the bottom line is we have a shapefile here that has a number of polygons, and those polygons presumably represent recognizably discrete vegetation units. They could vary in composition, they could vary in vegetation structure, they could vary in one or more abiotic variables such as terrain features. But generally, these stands, as you are probably intimately familiar with, are going to represent some kind of meaningful spatial unit on the ground. And hopefully that corresponds to something meaningful in the vegetation, because ultimately that's what we're going to focus on is how those vegetation patterns affect ecological processes. You may also have treatment units that may or may not correspond with the stand boundaries. In most cases, the treatments will probably correspond exactly to the stand boundaries. But in some cases, the treatment units themselves may combine multiple stands into a single treatment unit, or in some cases, they may subdivide stands or create entirely new boundaries. So here's an example with the red line superimposed on top of the treatment units within this overall project area. And if we zoom in, you'll see that in most cases, I'll turn that off and on, the treatment units overlay the stands. Now here's an example right here in the middle where the treatment unit has kind of subdivided that one stand into separate treatment units. But in other cases, such as this one here in the upper middle, you can see that treatment unit corresponds exactly to that stand. In other cases, a treatment unit may encompass multiple stands, that you see down here in the bottom. The lines don't overlap exactly, but essentially this treatment unit is basically combining these two stands underneath. So we are less interested in the treatment unit boundaries for this exercise. We're interested in it only insofar as the treatment units boundaries and the prescribed treatments will change the vegetation in the underlying vegetation stands. And we'll get to that in just a bit. But the bottom line is focus on getting a spatial representation of your data that focuses on meaningful vegetation units, okay, which for now we're just going to call stands, okay, such as you see here. Now, the stands are going to, typically be represented in a shapefile, and I'll open up that shapefile here. So by just right-clicking on this in the table of contents, and if I open up the attribute table, what you're going to see is most stands layers within the Forest Service and layers like the stands layer are going to be populated by a whole bunch of fields. And we don't really care about what all these fields are, but essentially each polygon is attributed based on a number of features. Now, this particular stands layer, which comes from the entire forest, is very poorly populated. In other words, most of the attributes, which you see as the columns here, which represent different vegetation attributes, different terrain features, and other things, are mostly empty or just mostly zeros, meaning there's just no data. And so that's really not that important for us. What is important for us or for you is that you have at least one or more attributes within your shapefile that does represent some vegetation attribute or attributes that is meaningful to you for the ecological processes or desired outcomes that you are interested in. So in this particular case, we have a field here. It's called Can-Cov Cree, and this is a quantitative estimate of tree canopy cover within each of these stands. You can see the numbers here, 20, 14, 43, 25, and so forth. And so each stand has an estimate of the tree canopy cover. Now that is something that we might be interested in terms of how canopy cover relates to some focal ecological process. In this case, perhaps having to do with the spread of wildfires, or alternatively, the movement and or suitability of habitat for a focal species, such as the Avert squirrel in this landscape. What you need to make sure is in your data set, you have at least one vegetation attribute, one field that is fully populated. In other words, you have values for all of your polygons. And it's okay if you have multiple vegetation attributes. In fact, it's even desirable. So you might not just have canopy cover, perhaps you have basal area, perhaps you have trees per hectare. So you may have multiple vegetation attributes. What is important is you have at least one attribute or a combination of attributes that you can use to create a meaningful depiction of the vegetation patterns that affect one or more focal ecological processes or desired outcomes of your interest. Let me just close this for a second and go back here. What's important to recognize is even though we have lots of stands here, I think there's maybe 84 or so stands in this particular project area. If I was interested in percent canopy cover, and I classified canopy cover into several classes as shown in the legend here on the left, then what we see here is I actually have some gaps in the data, which are private lands, which we either don't have the information on or we don't care about it. So I've just put them in gray here on the map and essentially just ignored them, if you will. And then we have a cover type here called grassland, shown here in this kind of light pinkish orange color, where there may actually be some tree cover, but we are going to depict this for purposes of representing vegetation patterns as perennial grasslands, where we're not really interested in tree growth in those polygons. And then we have three classes in forest cover, and it's all ponderosa pine forest in this particular landscape. So that the abbreviation for Pinus ponderosa or PIPO over here in the legend. And I simply classified this into three classes: less than 25% canopy cover, 25 to 50, and greater than 50. And that's what you see depicted here in the various shades of green. In the end, it's not the complexity of the stand boundaries that we really care about. Now, they give us the raw data from which to generate this pattern in this landscape defined by these five classes. But in the end, this is what we're going to see. Those stand boundaries are just there for the purposes of organizing the data. But in terms of the ecological effects of vegetation patterns, this is what the ecological processes see, not the actual stand boundaries. So this is ultimately what we really care about. Do we have enough vegetation complexity within our project area as depicted, in this case, by these 5 classes that I've defined over here? Do we have enough vegetation complexity to say something meaningful about the ecological processes of interest or the desired outcomes for this landscape? If, for example, I was interested in let's say a focal organism that its preferred habitat is this open canopy pine forest, as shown in this light green, that they forage and move through this, but they may require some higher canopy cover, some denser canopy for nesting and roosting. So their preferred or optimal habitat may be this open canopy next to this more moderate or higher density canopy cover. And so it's the juxtaposition of these classes that actually may be important. And so in this case, as you can see, we've got a lot of pattern here. We've got a lot of complexity in the distribution of this preferred foraging habitat and movement habitat in the light green. And there's a lot of edges with this higher canopy cover class, both in the medium green and the dark green. So there's kind of a lot of pattern here for assessing how this landscape might affect that particular process. So what's important for you, again, is yes, you need to have a lot of stands if your data comes in the format of stands. But ultimately, what you really care about is once you kind of dissolve those stand boundaries and look at just the vegetation patterns, that you have enough complexity here to say something meaningful about how that pattern may affect the ecological process of interest. Okay, so in this case, we clearly do. If the project area that you're currently working on, or maybe perhaps the project that you've just completed, doesn't quite have the complexity that you think is necessary, then it's going to be up to you to expand your project area to some larger extent where you can bring in or encompass more vegetation complexity. In the end, again, the boundary itself is not critical. Whether this corresponds to an actual project is not critical. What is critical is that you come with a data set that you're familiar with that has enough vegetation complexity to say something meaningful about how it affects or might affect the ecological process of interest to you. And again, remember, I have depicted this landscape and this complexity based on these 5 classes, based on canopy cover. If I were to use a different classification scheme based on a different vegetation attribute, perhaps let's say vegetation height class or developmental stage classes, I would see a different vegetation pattern here. And that's fine. It's going to be up to you to decide, what vegetation pattern you want to use or you want to represent in that landscape. And the choice will depend upon the ecological process that you think it relates to. If you have more than one vegetation attributes or vegetation patterns that you think relate to the process or desired outcome you're interested in, that's fine too. The more the merrier. You just need at least one. Okay, the other thing that's really useful when we think about vegetation patterns and process is to think about it in a comparative analytical framework. In other words, comparing a landscape to itself before and after treatment is very instructive. Or comparing a landscape prior to treatment to another reference landscape is also very instructive. Or alternatively, is comparing a landscape in its current state or after treatment to a set of desired conditions that have been specified for that particular landscape. The important thing here is that if you have any way to create a comparative representation or comparative analysis, you need to seek that out. One of the most straightforward ways to do it, and the way I would strongly recommend if you can, and this would be either if you have a project that you have recently completed, or if you have a project that's in the planning stage, but you've already kind of outlined the treatment prescriptions for all the units within the project area, but is to have within your shapefile, I'm going to open that shapefile back up. Within that shapefile, ideally have for each of those spatial units, again, the polygons, or in this case, the stands in our landscape. I'm going to turn that off. In addition to having the condition before treatment, which is this column here, the canopy cover class before treatment, we also now have after treatment, have the canopy cover class change based on implementing the various prescriptions in those treatment units. So, you'll need to basically, or if you adopt this scenario, this comparative analysis scenario, you'll basically need to create an attribute within your shapefile that shows the change in that vegetation attribute before and after treatment. Okay. And again, you may have multiple attributes before treatment, and then again, ideally, you'd have those same attributes after treatment. The other thing to think about is if you have an attribute table for your stands layer that has several vegetative attributes of interest, diameters and tree heights and densities and basal areas and tree species composition, etc. Feel free to think about how you would combine those into a meaningful classification scheme to represent patterns on the landscape that relate meaningfully to your focal ecological processes or desired outcomes. And ideally, you will complete that combining of vegetative attributes prior to coming to the course. In other words, let's say you have 3 or 4 columns of data that you want to combine into some meaningful classification scheme. Well, you need to work with your GIS tech assistant or expert if you don't have the skills yourself, but basically do the field calculations needed to combine those attributes into a new field that represents the vegetation patterns you're interested in. But most important is if you do choose to do that, make sure you try to get the field as populated as completely as possible. In other words, you want to have every unit ultimately to have a final value. It's not ideal to have a situation where you only have a handful of the units with information and the rest of them are missing, because then you're not going to end up with the vegetation pattern complexity that you need. So it's okay if you have some missing polygons. For our example, we have these private polygons here that we basically are just leaving as nothing or unknown or don't care. And that's okay because they're just a minor part of this landscape. You just want to make sure that most of the landscape has data. So again, think about the processes that make that are most important to you on your home unit. Again, whether those are disturbance processes, whether those are focal species concerns, whether those are general things like ecosystem resilience or biodiversity, or could even be something very specific such as aquifer recharge. I mean, the sky's the limit here on the kinds of processes and desired conditions that might be relevant to you on your home unit. But whatever they are, just do your best to make sure you have one or more ways of representing the vegetation patterns that relate to it. And ideally, you have a scenario analysis where you can look at pre and post treatment. Now, I recognize that a lot of you won't have a pre and post, and that's okay. What's most important is you have a good representation of the spatial patterns prior to implementing the treatments, and you can relate those meaningfully to your focal processes or desired outcomes. But if you don't have a pre and post, either because you haven't implemented the treatment yet, or because you haven't quite figured out what the treatments are going to be on all of your units. You know the current condition, but you don't know exactly how they're going to change. Then see if you can find a reference landscape for comparison. So another landscape that is comparable in size and complexity, but perhaps represent some reference or desired condition that you're trying to achieve in a general sense with your project landscape. And in that case, you need to have two data sets. You need to have one of your focal project landscape, and then a very similar data set that has the same vegetation attributes populated for your reference landscape. And if you have neither of those two comparative analysis scenarios available to you, so you simply just have a single project landscape with one or more veg attributes that does show some meaningful vegetation complexity that you can relate to one or more focal processes or desired outcomes, but you don't have a before and after, you don't have a reference landscape, then you need to seek out, if they're available, desired conditions for the vegetation patterns that you're trying to achieve with your treatments. And so it may be a set of desired conditions written for the forest as part of the forest planning process that describe things like what percent of the landscape you want in each cover type, or what percent should be in each developmental stage, or basal area class, or canopy cover class, or whatever it may be. And maybe there's also some description of some target ranges of variation in patch sizes and arrangements, things that we'll talk about in detail in the course. But having a set of targets in the composition and spatial configuration of your vegetation patterns that you can then use to see if where your current landscape falls in relationship to those targets, and thus what you might need to do to move that landscape towards those targets. So again, think hard about finding a way to make your home unit project a comparative analysis in one of those ways that I just mentioned. Okay. In addition to having this project database that includes this shapefile with vegetation that we've just been discussing, what I also have asked you to do is have at least one or more better, layers that show you the abiotic environment that may help you explain the vegetation patterns you see today, or that you think drove vegetation patterns in the past, or that you think may influence vegetation patterns going forward in time. And those abiotic layers can be anything, but at a minimum, I would think you'd want to have an elevation layer, such as you see here, to show the basic terrain. Because we know that terrain is going to play a strong influence, either directly, but more often indirectly, on the vegetation patterns in your landscape. So having an elevation layer is probably a must, I would say. But you may also have things derived from elevation, such as aspect, as shown here, classified into kind of the 8 cardinal directions plus flat. You may also have a layer on slope that looks at, slope as a percent, showing where you have steep slopes, where you have relatively flat areas. That could also be very important in driving vegetation patterns. Or things derived from the elevation surface that take into account aspect and slope, such as topographic position index. So where are you topographically in relationship to the ridges and valleys? Here, the bluer areas being the kind of the valley bottoms, and the redder areas being more up on the high points of the ridges. Something like this is the solar radiation index. It takes into account where you are latitudinally, but then also where you are in terms of slope and aspect relative to the primary sun angles during the growing season. So where you're receiving, relatively more or relatively less solar radiation, that may be important in affecting growth in your area. Or in this case, topographic wetness index. So where is water most likely to collect and produce kind of wetter growing conditions versus more xeric growing conditions. Perhaps you have soil data that's important in your area. Maybe soil depth, as shown here, is important or plays a role, or perhaps it's soil pH that plays a role, as shown here. So again, there's no limit to the kinds of abiotic variables that you might contemplate as to how they may influence the vegetation patterns, how they played a role in creating the patterns you see today, how they may influence where and what kind of treatments you do to change the landscape, and how they may influence the changing vegetation in the future. So what I've asked you to do is have at least one, probably elevation at a minimum, but more the merrier. The more things that you can bring in to help you explain your vegetation pattern and process relationship, the better. And you don't have to stop at just abiotic layers. You may also bring in things like disturbance history. And in this particular landscape, we might be interested in both wildfires as well as a variety of bark beetle insects disturbance processes. This is just showing you where the historical fires, at least within the past 100 years, have been within this landscape. So as you can see, we have not had a lot of burning in this landscape, just 4 fires over the past 50 or 60 years. But most of the area is unburned. And this is a huge departure from the historic processes in this landscape. And again, we'll talk about this more in the course here. But I could also bring in, I haven't done it yet, but layers showing mapped insect outbreaks over a period of years. So any kind of disturbance process data that you may have may also help you better kind of explain the vegetation patterns you have today, what you might do to treat them, and where the landscape may be going in the future. Okay, the other thing that I mentioned in the write-up is to make sure that your data, your primary data. So let's go back to our stands shapefile, and I'm gonna open up the properties of that. So if I right-click on it and go down to properties, I'm gonna go to the properties here, and I'm gonna look at spatial reference down here on the right. Okay, and what I want you to make sure is that your data is projected. It has a projected coordinate system. So just to clarify that, and most of you probably are already aware of this, but there's geographic coordinate systems and projected coordinate systems. A geographic coordinate system basically tells you where you are on the world, on the globe. Okay, it tells you where geographically you are located. And then the projected coordinate system basically tells you how to take your data and project it onto a flat surface, recognizing that the surface is actually not flat because the data actually exists on the globe. So if you look at the spatial reference information in your data layer, you want to make sure your data has been projected. And if it has, it's going to say projected coordinate system, and it's going to tell you what that projected coordinate system here is. This happens to be a UTM coordinate system for this zone, which is a longitudinal zone, that is a relevant projected coordinate system for use in the Southwest in the US and elsewhere. The important thing is you want to make sure your data has been projected, okay, into a coordinate system. Okay, it's also going to have a geographic coordinate system. Again, this is just saying where you are on the globe, but not how to represent it on a flat surface. And we need to represent our data on a flat surface because we're going to basically treat the map as a flat surface when we analyze the vegetation patterns. So if you have data that's not projected, you will not have this top part. You'll only have this geographic coordinate system information. And essentially, your spatial data will all be in latitude and longitude, which is great for telling us where we are, but doesn't help us actually map it onto a flat surface. So bottom line is make sure your data is projected. It doesn't matter what projection you have. Your forest or your region will have adopted some standard for projecting their GIS data, and hopefully they've adopted the same projection so that all the data is consistently projected. It can be a nightmare when different projections are used and you're trying to combine data sets when different projections are used. So in modeling, we almost always first check projections and project them all the data to the same coordinate system. That's the only way you can combine layers in a meaningful way. So you just need to make sure that your data has been projected. Your linear unit should be meters. And you also, and that's basically what you need. That's all you need to know is that it's projected and you've got meters as your linear unit. Okay. Now, there may be some of you that actually have data in a raster format. So instead of this polygon format where the data is packaged up by polygons, you may actually have data that comes as a raster. And we'll be talking a lot more about that, and we'll be working with raster data a lot in the course. But the raster data, of course, instead of having the data packaged into polygons, has the data values associated with individual cells. So generally square cells in a grid across your area. And each cell has one or more values for whatever attributes of interest there are. And so if you have raster data, okay, this is actually a more ideal way in the end to deal with the data. We'll again talk about that in the class. But if you look at the attribute, if you look at the spatial reference system for raster data, okay, if we open up the properties for this data set and we look at the raster information here, okay, one thing we're going to look at is cell size. And we want to make sure that your cell size is square. So here I have 5 and 5. So because it's a metric projected coordinate system and the linear unit is meters, this is saying we have a 5 meter by 5 meter square cells. And what's important for us for analyzing the data with a couple of the software tools we'll use is that we have perfectly square cells. And sometimes, based on the geoprocessing steps used, the raster data comes in with not perfectly square cells. Even if it's out to the several decimal points, they need to be perfectly square. If you are using raster data to represent your vegetation, okay, you're not coming in with a shapefile, you're going to come in with raster data representing some vegetation attribute that you're interested in. Just make sure you check first that it's been projected, and then second that you have perfectly square cell sizes, okay? And if we go up here, let's see, let me close this raster information. We go down here to spatial reference. We'll also see that it has been projected. Whoops. It has projected using the same projected coordinate system as the shapefile. Okay. And that the linear unit is meters. Okay. All right. So that's for raster data. All right. The last thing is if you feel like you cannot generate a data set like what I'm showing you here, and it doesn't need to be exactly like this in any ways, just based on, the ideas that I've presented today in terms of vegetation complexity in one or more attributes, and ideally with a comparative analytical framework scenario analysis. If you feel like you just don't have that, then you can partner up with somebody else in the NASP course, ideally from your forest, or probably more likely from your region, since rarely do we have more than one person from the same forest in the class. But you can reach out to other NASP class members from your region and see if they have a data set that meets these conditions, and you can work with them on that data set. The important thing is that you're working with a data set in an area of the world that you're familiar with. So you understand the vegetation, you understand the abiotic environment, you understand the ecological processes that operate there. You kind of understand generally, even if it's at the regional scale, what the desired outcomes are, and so forth. And last case is if you simply cannot if you cannot generate your own data and you've reached out, you can't find anybody who's willing to work with you, then you need to email me and let me know, and we'll find an alternative for you. Because I do have some data sets that could be made available, but that's not ideal because they're not going to be data sets that you're familiar with. And as you'll see in the course, your familiarity with your data is going to be really important for you to get the most out of the exercise. Okay, I think that's all I wanted to cover today. I hope this all made sense. If it didn't make sense or you still have questions after this and after rereading the pre-work document, which goes over this in detail as well, reach out to me and reach out to me sooner than later. You really want to get started on this right away. You really want to reach out and get the assistance you need from your GIS people if needed. If you don't have the GIS skills to do this, reach out and get the assistance you need. And don't procrastinate. Don't wait till the last minute, because your enjoyment in the course and how much you get out of the course will in a large way depend upon how well you come prepared with a data set of your own. Okay, that's it. Thanks for your attention today, and I'll either see you online or I'll see you in January in Flagstaff. Okay, take care, everyone.